All right, so last time we looked at 7.2 part 1, so you're going to look at 7.2 part 2. Okay, still talking about inverse trig functions. And the goal here is we're going to take a trig function, okay, something that has sines and cosines or inverse sines, whatever it has, and we're going to convert it to an algebraic expression. All right, so why you'd want to do something like that is because if you can eliminate all the trig functions from something and just make it pure algebra, adding, subtracting, square roots, squaring, somehow you can come up with a formula that does the same thing without using any one of those three buttons. Okay? You can do a lot more with that formula. Okay? Especially in calculus, it makes finding derivatives easier, integrals easier, because you have an algebra formula rather than a trig formula. Okay? You can't convert everything in trig to algebra, but what we're going to do today, you can. So what's going to happen is we're going to have two functions, one inside the other, kind of like we did in section 7.1 part 1, 7.2 part 1. Okay, we'll have a trig function on the outside, and then we'll have a different one on the inside. Okay, for most of the problems that we deal with, we're going to start with the inner trig function. And we're going to try to take that inner trig function and represent it as a diagram. Okay, we're going to try to visualize it. Okay, this is especially helpful when the inner trig function is an inverse trig function. Okay, so when the inner one is an inverse trig function, this is what you want to do. Okay, and another trick we'll use is we'll rewrite that inverse trig function as a regular trig function. Okay, for example, if I had let's say inverse sine of x equals y. That's exactly the same thing as saying this. There's no difference between those two equations. All I did was take the sine of what was on the left and take the sine of what was on the right. So that's what I mean by taking an inverse trig function and rewriting it as a regular trig function. Okay, and the last thing that'll come in handy is the Pythagorean Theorem. And we'll keep in mind any angle restrictions that we have with inverse trig. For example, inverse sine is between negative 90 and 90. Inverse cosine, 0 to 180. Inverse tangent, negative 90 to 90. But be careful with the asymptotes. You can't include the endpoints. If we need to, we'll go back to that page in the previous section where we have all that stuff written down. All right, so let's take a look at example. Okay, so our first example says the sine of the inverse cosine of v. Okay. What I want to do is come up with a formula to do that. Purely algebra. I don't want to have any trig functions in it at all. Right, so it says the key is we're going to start with the inner trig function, which in this case is inverse cosine. What kind of answer do you get? When you take inverse cosine or inverse sine, you type in a number and you hit enter. That number that pops up on the screen, what does it represent? Think back to right triangle trig. You only had to use inverse trig when you were trying to solve for what? Anyone remember that? Did we have to use inverse trig? Okay, how about Pythagorean theorem? Kobe, when would you use Pythagorean theorem? If you're trying to find a side. Okay, Pythagorean theorem you'd use if you're trying to find a side. So inverse trig you use when you're trying to find, what else does a triangle have besides sides?
Angle.
Angles. Okay, inverse trig is used when you want to know an angle. Okay, if I drew this, and I said, find this angle, I could use opposite and adjacent. I could use inverse tangent, okay, to find that angle. Pythagorean theorem wouldn't help me find that angle. All right, so let's start with that. Okay, we've got inverse cosine of v. I don't know what it equals, but I know it equals an angle, some angle. So for now, I'll just represent that angle as theta. Okay, so that whole thing is theta. Okay, the next part, I'm going to take and rewrite that inverse trig function using regular trig. So to do that, I'm going to take the cosine of each side. That's going to get rid of inverse cosine. Take the cosine of what's on the left. Take the cosine of what's on the right. And now we have v equals cosine theta. Now this is what I want to draw a picture of. I want to draw a right triangle. Put theta wherever you want. I'll put it at the bottom. And I want the cosine of this angle to come out to v. So first of all, we got to remember what two sides are in the definition of cosine. So your choices are opposite, adjacent, and hypotenuse. So, James, remember? Adjacent and hypotenuse. So this one and that one. Can you give me values that I could give these sides so that if I take the cosine of this angle, it comes out to v? Try to think as simple as you can. You want to assign the bottom side a value and the hypotenuse a value so that when you do adjacent divided by hypotenuse, the answer comes out to v.
What is v?
V, we don't know. We're not going to know what v is. So the values that you pick for these sides might not be numbers. Might use some numbers, but you might also just use letters. Anyone help them out? You can pick anything you want, as long as whatever you put here and whatever you put here, when I do adjacent over hypotenuse, the answer comes out to v. There's infinitely many answers, but I think there's one that's simple. Yes. If I assign those two sides, then this is going to make the adjacent v, the hypotenuse is 1. Adjacent over hypotenuse, v divided by 1 is now v. Okay. Now the last algebraic part here, I need this side. Okay. What theorem is going to help me to find the third side in that right triangle? Because I've got two. Now I need the third one. Victoria? Yeah, the Pythagorean theorem. So I'm going to use the Pythagorean theorem. For now, we can, if you want to call this side b, I'm going to cross that out in a second because I'm about to know what b is. Okay, let's fill in the Pythagorean theorem. b squared plus b squared equals 1 squared. Now solve for b. So we're going to subtract v squared. We get b squared equals 1 minus v squared. My last step, Jill, how do I get rid of that exponent on b?
Square root of both sides.
Yep, take the square root of both sides. So b is the square root of 1 minus b squared. Okay, so let's fill that in. Now this diagram is going to be the key to finishing the problem. This is all we need now. Now our original problem said to take the sine of this thing, right here. This thing that I just circled is that picture. Okay? I drew this inverse trig function as a picture. So now I want the sine of this picture, right? Using theta as my angle. Why theta? Because we said this inverse cosine is theta. We did that at the very beginning. Okay? So we're using that angle. Okay, so Augustine, what's the definition of sine? It's a ratio of what two sides?
A ratio of the opposite over the hypotenuse.
Yep, it's the opposite over the hypotenuse. All right, so to get an algebraic formula, we need the sine of our picture, which we just drew. So the sine is opposite, square root of 1 minus v squared, over hypotenuse in this case is just 1, so we don't need to write divide by 1. So there's an algebraic formula if you want the sine of the inverse cosine of something. Okay, let's try it. Let's type it into our calculator. Let's look at the table and see if it works. Right, so we have sine of inverse cosine of x. Okay, now remember, inverse cosine has restrictions on what you can plug in. Okay, we can only go, let's go back and look at our restrictions. Oops. Okay, inverse cosine, we got to pick values between -1 and 1. All right? Now let's type in our expression. Square root of, was it 1 minus x squared? Okay, we use v, but again, when you type it in to check it, you got to use x. Let's go to our table. Of course, we're going to get a lot of errors if we pick things that are outside -1 to 1. So let's make it so we can type in what we want. Right, let's try 0.5. Okay, get the same thing, 0.866. Let's try -0.78. Get the same thing with each formula. 0.94. 0. Okay, no matter what we plug in, we get exactly the same thing. So we just found an algebraic formula from a trig expression. Any question on that? Let's try another one. Okay, you could have any regular trig function on the outside and any inverse trig function on the inside, and you could do this. Okay, let's try the tangent of the inverse sine. Okay, so we want to get an algebraic formula. All right, who can tell me my first step? It's the very first thing I should write down. How about Cody?
The inverse sine of v is equal to theta.
Good. Inverse sine of v is equal to, well, it's going to be an angle. We don't know the angle, so let's just pick theta. Okay, Andy, what's my next step?
Multiply each side by side.
Well, be careful, it's a function, so multiplying only applies to variables and numbers. Can't multiply by a function. It's like if I said to you, multiply each side by square root. Did that make sense there? Now, how do we say it? No, you can't divide by functions because they're not variables or numbers. Just somebody tell me, how would you say what to do on each side here? Not multiply by square root, but
Take the square root.
Take the square root of each side. Take the sine of each side. Okay. So I know what you meant. You're on the right idea, just how you were saying it. So if you take the sine of each side, you get this. Okay. Now my next step is to change this equation into what? What do we want to do from here? Yep. I want a diagram now. I want a diagram so that when I take the sine of an angle, the answer comes out to V. First thing I have to decide is what two sides am I going to be using? Cole, what sides do we use for sine?
Opposite.
Yep, we're going to use opposite and hypotenuse. Anybody give me some values? It's going to be very similar to last time. But give me two values I could use, one for the opposite and one for the hypotenuse. So when I fill them in, the answer comes out to V. About Kobe?
1 and V.
Okay, which one do you want to make V?
Hypotenuse.
Okay. Which one do you want to make 1?
1 below.
All right, like that? Right, two things with that. Anybody tell me one thing that's off with this? Yeah. We didn't use the right sides. Okay, so for sine, we definitely want to use opposite and hypotenuse. So those are the two we got to stick with. Right? So the 1 and the V were correct, but we have to flip them. All right. Now, if we take the sine of theta, opposite divided by hypotenuse, V divided by 1 comes out to V. Okay, Emily, what do I do to get this bottom side? We can use the Pythagorean Theorem. If you want to pick any letter you want, we're going to erase it in a second. We have a squared plus v squared equals 1 squared. And now solve for a. So if I subtract v squared and then take the square root on each side, I get a is the square root of 1 minus v squared. So you're going to notice that pattern a lot. You get that 1 minus v squared, something like that. Okay, you'll see that a lot. Okay, now our last step. We want the tangent of this angle. Remember, sine of theta, inverse sine of v, we represented by theta. Right, so really we're taking the tangent of theta. So now go down to your picture. Tangent. Jill, what two sides do we use for tangent?
Opposite and adjacent.
Opposite over adjacent. So it's v divided by the square root of 1 minus v squared. Okay, now algebraically that is correct. The only thing they might do is clean it up and get the square root out of the bottom by multiplying top and bottom by square root of 1 minus v squared. Okay, so our final answer, we're going to get v times the square root of 1 minus v squared divided by 1 minus v squared. Okay, again, so there's an algebraic formula to take the tangent of the inverse sine. Okay, any questions on that one? Every problem like that is very similar. That's how you do pretty much all of them.
You go back.
Now, some people can think some of that through in their head. They don't need this diagram. They can just visualize it, do the Pythagorean theorem in their head. If you can, that's fine. But I think for some people, it's kind of a lot to do all in your head. All right. I'm going to skip over this one. Okay, it's pretty much the same as the other ones you did. Start by writing inverse tangent x equals theta. Rewrite it so it's x equals tangent theta. Draw your diagram. Use Pythagorean theorem. And then once you have your diagram, they want the cosine adjacent over hypotenuse. Okay? I'll leave that one for you guys. Okay, this one's a little different. This one says evaluate. When they say evaluate, your answer is a number. Okay, so they want to know the number. All right, so just like anytime you have PEMDAS, you're always going to start with the inside expression and work your way out. Now, I've set up this problem to be very special. In general, you can't do this kind of problem in your head unless special things happen. Okay, so let me show you what's going to happen here. Let's start with the tangent of 3 pi over 4. I'm going to try to figure this out. Okay? And 3 pi over 4 is a special angle, so I can do that in my head. I'll show you how.
What was that practice problem?
The practice one? It was number 48 in the book, page 395. All right, so let's see if we can figure out the tangent of 3 pi over 4. First thing I'm going to do, just to visualize it, I'm going to draw it on a unit circle. Okay? And I'm going to convert that to degrees. Or let's see if we can do it in our head. What's pi over 4? Anybody remember what that is in degrees? Pi over 4? Augustine?
270 degrees.
That's 3 pi over 2. 270 is 3 pi over 2. Okay, how about pi? Anyone remember how much is pi in degrees? Yep. 180. Okay, so what would pi over 2 be? Let's take half of it. 90. Now let's take half of pi over 2, which that's pi over 4. What's half of 90? 45. So pi over 4 is 45, and now we're tripling pi over 4. Okay, 135. Okay, let's sketch that. Okay, Casey, where would 135 be in that diagram? Yeah, in between, well, can you be more specific than, no, actually, no, that's good enough. Between 90 and 180, it's exactly halfway. Yeah, it's exactly halfway. Okay, so when we say 135, we're talking about this angle right there. That arc, which corresponds to that angle, since it's a unit circle, is 135. Okay, let's draw that triangle a little bigger. Okay. Brielle, how much is this angle right there?
45.
So that means this one is how much?
45.
It's a 45. So this is a 45, 45, 90 right triangle. Does anybody remember the length of the two legs? The hypotenuse is 1. And what's the length of each leg? It had square roots in it.
Is it like 2 square roots of the hypotenuse?
It does have a square root of 2 in it, so we're getting there. But it's the square root of 2. Yep.
Hypotenuse times the square root.
It's not the hypotenuse times the square root of 2. Remember, Darren?
The square root of 2 over 3.
Yeah, square root of 2 over 2. So we were close. And now I'm going to take the tangent using that as my reference angle. Okay? I've already drawn the triangle, so it's correct. Remember that the bottom side, think of as negative, because it's going left. The height, think as positive, because it's going up. So it's left and up. Okay, so tangent is opposite divided by adjacent. So in this diagram, what would you get if you take opposite, divide by adjacent? Make sure you take into account the directions.
And do you have one?
Not one. Anyone remember? Think of this diagram too. Tells you which trig functions are positive in which quadrant. So in quadrant 1, they're all positive. In quadrant 2, the only trig function that comes out positive is sine. So we can't get 1 because we're taking tangent. What would we get? Kelsey? Negative 1. Remember, take into account the direction. You're going left. So that's a negative divided by a positive. If you want to write it in your diagram like that, you can. Negative, positive. All right. So the tangent of 135 is negative 1. So now we know this. Let's rewrite our problem. Now we just have to figure out the inverse sine of negative 1. Okay, for this part, what I would do is, you can think of it like this. It's going to be equal to an angle. That's your answer. It's going to be an angle. So you could think of taking the sine of each side. And I'm asking you where the sine function hits negative 1. Where does the sine function hit negative 1? Okay, for that, let's sketch it. So we've got marks. This is positive 1, negative 1. Anybody tell me where sine hits negative 1? What's the angle? But Alex?
135.
No, not 135. We talked about this when we did the sketches. These are like the key points, and they were all separated by 90 degrees. So this is 0. You hit the highest point at sine at 90. And then from there, Jill? Yeah, 270. When you're at 270, that's when, if you take the sine of it, you get negative 1. Right, so the answer to this, 270 degrees. Now, if it didn't come out to negative 1, if say it came out to where does the sine hit 0.74? Okay, that would be tough to figure out in your head. You couldn't do it. You could tell me where the sine hit 0, 1, or negative 1. Those are the only 3 you could have done in your head easily. Any questions on that? All right, so we started with that inside function, used unit circle trig to figure out what the tangent was. And then we used the diagram or the graph of sine to go from there. All right, let's try. Anybody have a preference? We can do one of these two. We can either do cosine of inverse tangent of a half or cosine of inverse sine of a half. Anybody care which one we do? Well, let's see, the last one we did sine and tangent. Let's do the cosine and sine one. Okay, so let's do cosine of inverse sine of a half. Okay, I'm going to start with that inside function and see if I can figure that out. Okay, now keep in mind here, the one we just did had the inverse on the outside, regular function on the inside. Well, now we're switching it. The inverse function is back on the inside. So I'm going to treat this exactly like the first two problems we did. I'm going to start with that inside function. This is even easier because instead of giving you like a v here, like I did in the first two problems, I'm giving you an actual number so you can figure it out. But you're going to do the same exact thing we did for the first two. Okay, inverse sine of a half, it's going to equal an angle. Now, I'm never going to find out what that angle is. That's not the question. I don't care what the angle is. I care what the cosine of the angle is. So we don't actually need to find that angle. Okay, what would be my next step here? I'm trying to make it so I can eventually draw this as a right triangle diagram, but I've got to rewrite this equation a little bit. Alex, how would I rewrite that?
As 1/2
Yep.
sine theta.
1/2 equals sine theta. Perfect. Now you're going to draw a diagram, put theta in it, and when you take the sine of it, I want it to come out to 1/2. James, what two sides are going to be involved if we're using sine? Good. Opposite and hypotenuse. Cole, what could I make the side opposite? You could. Okay, you could make it a half, but then that's going to make the hypotenuse a little harder to figure out. I want to put a number here and a number here, so when then I do opposite over hypotenuse, I get 1/2. Yeah. 1 for which side? Yep. And what else? 2 for hypotenuse. And how do we get that third side? Yeah, the Pythagorean Theorem. Okay, so we're going to plug it in, find the third side. We're going to get a number. We're not going to have a variable expression. All right, so I'll just do it quick. You're going to get square root 3. Okay, now remember, inverse sine, we said that's theta. I really want the cosine of theta. Okay, Colby, what's the cosine of theta? Yeah, very good. That's it. So the cosine of theta, which is the answer to the original problem, square root 3 over 2. Okay, and to do all that work, we never actually found out what theta was. We could if we wanted, but that's not what they asked for. Okay, any question on that one? So very similar to the first two, except it's all numbers instead of letters. So I kind of started you guys off with the harder one. I think the numbers are the easier one. All right, so last thing we're going to do is look at solving some trig equations. Okay, we can use the graphing calculator if we need to. We'll also try to do it algebraically a little bit. Okay, remember that trig equations are periodic. So that means if you have one solution, you have infinitely many solutions. Okay, that solution reoccurs every period. Okay, just to review how long the periods are. Augustine, what's the period for sine? Do you remember what the period measures? Not what it is, but what it actually measures on the graph? Okay, it is measured in degrees. It's the length of the time before the function repeats. Anybody help them out? What's the length of time in degrees before that function repeats? 90 only gets us a quarter of the way there.
Oh, 360.
360, or 2 pi. Okay. How about the period of cosine? Yeah? How much? So cosine looks like this, and pi gets us to right there. 3 pi over 2 gets us right there. Help her out. What's our period for cosine? So pi over 2, pi, 3 pi over 2. Gotta go one more mark over, keeping the spacing the same. Yep?
2 pi.
2 pi. Sine and cosine have the same period. Okay. So do their reciprocals, secant and cosecant. What about the period of tangent? How often does tangent repeat? Okay. Might want to think of those formulas we had for, I think we wrote it like this. 2 pi over b. That was the formula to calculate the period for sine, cosine, secant, and cosecant. And then we had a different formula for calculating it for tangent and cotangent. That number in the top is the period. Does anyone remember what other number we had? Yeah? Oh, Cody? Pi. Period of tangent and cotangent is pi. All right? And there's one more thing I have to throw at you too. I have to know which trig functions are positive in which quadrants, and I have to know how to use the reference angle to find the other solution. Okay? So in quadrant 1, all your trig functions are positive. In quadrant 2, it's just your sines. In quadrant 3, just your tangents. In quadrant 4, the only trig function that comes out positive is cosine. And that's also true for the reciprocals. The reciprocal of sine comes out positive in quadrant 2. Reciprocal of tangent comes out positive in quadrant 3, and so on. Flipping a fraction doesn't change its sign. Right. And then we have to know how to work with the reference angles. So just as a quick reminder, if you're in quadrant 2, and you get one solution, and your other answer is in quadrant 2, it's 180 minus your reference angle. If you're in quadrant 3, and you already have one solution, it's 180 plus that solution, or 180 plus your reference angle. Does anybody remember how we do it in quadrant 4? If we had one solution, and our other solution is in quadrant 4, how do we find it? Yep.
360 minus
Yeah, very good. 360 minus the reference angle. Okay. So we got to keep all that in mind to find the second solution. If we don't, we might miss half the solutions to every problem. Okay? So let's try it. Okay, so this says to find all real solutions. Okay, so in my head, if I kind of want to estimate how many solutions there are per period, I could do something like that. This is 1. This is negative 1. 0.6 might be about right there. I'm looking for 2 solutions. Let's use the calculator to get one of them. Who can tell me what I need to do to each side to get rid of sine? and get x by itself? About Brianna?
You did times by the inverse sign.
Do the what on each side?
Inverse sign.
Inverse side, and you said times each side by it?
Do the inverse sign.
Yeah, take the inverse sign. Remember, inverse sign is a function. You can't add, subtract, multiply, or divide with a word. Only with variables and numbers. Okay, so we'll take the inverse sign. It's on the left. Take the inverse sign of what's on the right. And what you're really doing is you're taking this number and plugging it into a function. So x is the inverse sine of 0.6. Okay, so let's get one solution. And let's make sure we're in degrees. Yep. So one answer is 36.87. If they wanted radians, I just would have switched to radians. Okay, now here's where we have to remember that diagram and how to find the second answer. We're dealing with sine. We're trying to find where the sine is equal to a positive value. Quadrant 1, 3 at 36 degrees is in quadrant 1. What was the other quadrant where sine comes out positive? 2, 3, or 4? Kelsey? 2. So now we know we have to be in quadrant 2. How do you find the second solution if your answer is in quadrant 2? Take your reference angle, which is 36.87. And what do I do with 36.87? Yeah?
Can you add it to 90 degrees? And then
Yeah, not adding to 90. Don't add it to 90. Yeah?
subtract it from 180.
Yeah, we got to subtract it from 180. So it's 30. Let's do it this way. That is the other solution. 143.13. And even after all that work, I'd still mark something like that wrong. Because it said to find all, not just 2. So just a small thing we need to add on to that. Does anybody remember, how do you represent all the solutions? This is where the period is going to come in. Yeah?
So just make it into like an equation.
I just need to put plus something on the end of that. So I'm going to get this answer, but this answer is going to reoccur every period. So think about if it keeps going. It's going to occur again there. It's going to occur again there. It's going to keep reoccurring forever. So how far apart are those two answers? Yeah?
Plus
Plus how much?
2 pi.
We could use 2 pi if we were doing radians, but we did this in degrees.
So this is
Okay, so now you've given me just that answer, but close. Plus 360. Because now I've got the answer 396.87 if I just add those two together. But it could reoccur any multiple of 360 going in each direction. So how do we account for that? Okay, think about how you would write all the multiples of 2. Anybody give me an expression that would represent every multiple of 2. You could just plug a number into it, and this expression could give me every single multiple. Yeah?
360
Yeah. Okay. So what I was thinking of is something like 2k. That's an expression that you could name any even number in the world. I could pick a value for k and do the calculation out, and I could get your number. So this represents every multiple of 360 that you could add or subtract from the two original answers. So this is what they're looking for. And if you want to double check it, you could graph it, calculate the intersects, and you'll see that the two intersects do occur right where we found them. In fact, I can do it real quick. Yeah, Augustine.
Well, you have to say that k has to be a whole number.
Yeah, technically we should say k, not even a whole number, is an integer. That way we can include negatives as well. So k is any integer. But that's important. Yes, thank you. All right, so let's graph the original problem and see what we got. Sine of x, 0.6. Now remember, we're just focusing on the first period. Those are the two answers we just found. Second calc. Intersect. Okay, there's one answer, 36.87. Yep. And let's go over and get the second one. 143.14. 0.13. So there's something, the way we rounded, but that's okay. Okay, any question on that? So that kind of question ties in a ton of stuff you have to know about which trig functions are positive where, how do you work with the reference angle, using inverse trig, okay, stuff like that. Let's finish up with this one. Cotangent of x equals 2.5. What would we like to be able to do there? Very similar to what we did in the last problem. Yep.
Of x by itself.
We want to get x by itself. So how could we cancel out the cotangent function? Which function would cancel out cotangent? Like which function cancels out sine? Victoria?
Wouldn't the inverse?
Yeah, inverse cotangent. It's exactly. We ideally would like to be able to just do this. Take the inverse cotangent. You can write this down, but watch what happens. So we're going to do that. We get x equals inverse cotangent of 2.5. Okay, great. Let's try to type that in on the calculator. Where's my inverse cotangent button? Yeah.
Punch into the 1 over this.
Well, we got to do something. We don't have an inverse cotangent button. So the thought we had is when we had tangent before, let's say you had tangent and you wanted cotangent. You took the answer and flipped it. Okay, we flipped it. Just like if you had sine and you want to know the cosecant, take the answer for sine and flip it. Well, it doesn't quite work the same. There is flipping involved, but not quite what you would think. Okay, so I'm going to try to get a different formula for x. One that doesn't use inverse cotangent, so then we can actually go through and figure out everything we still need to figure out. Let's go back to the original problem. Cotangent x equals 2.5. Which trig function do you think I'm going to change this into? I have a cotangent right now. When we start to flip things, what trig function would be used here if we start dealing with reciprocals? Yeah? Tangent. Okay, so we're going to convert this somehow into tangent. The way we're going to do it, if you have the answer to the cotangent and you flip it, now you have the answer to the tangent. That's a reciprocal identity. Now I've got an equation that I can get x by itself using an inverse trig function that I actually have a button for. Okay? So now let's take inverse tangent of each side. And inverse tangent. So now we get a new but equivalent expression for x. It's the inverse tangent of 1 divided by 2.5. Okay, what I have in the boxes is exactly the same thing. So there is flipping involved, but you're flipping the argument. Okay? You're flipping the argument. We didn't do that here. It's not like we said tangent of 1 over x. We flipped what it was equal to, not the argument. Right? So that's how you do inverse trig when it's inverse cosine, inverse secant, inverse cosecant, or inverse cotangent. Okay, so just off to the side, if I had this, I needed the inverse secant of 0.3. Well, think in your head, which trig function do you get when you flip secant? That's cosine. And we're dealing with inverses. And flip the argument. That's how you would do this. The inverse cosine of 1 over 0.3. Okay, so now we can actually go ahead and find our answers. Okay, and if you don't have a graphing calculator, you don't need one. Okay. Take 1 divided by 2.5. Take the inverse tangent, and we're doing it in degrees again. So 21.80. Okay, what's my period of tangent? Remember, tangent and cotangent's a little shorter than the other ones. Emily? Well, 2 pi is for sine and cosine and secant and cosecant. Tangent and cotangent's a little shorter. Sure. James? Pi or 180, so he said 180, which is good because we're in degrees. And what do I need? Plus 180 k. Technically, that's degrees as well. Okay, so there's one answer, and it's going to reoccur every 180 degrees. Okay, it can be positive or negative, integer. Okay, now I need the other answer. Well, the other answer is still going to have a plus 180k. If we go back to the very beginning, we're trying to find where the tangent or cotangent equals a positive number. Same thing. Which quadrant is tangent positive in? Quadrant 1. And what's the other one? 3 up? 3. We're in quadrant 3. Who can tell me, what do I do with my reference angle in quadrant 3? Yep.
You add that by 180.
All right, we're going to add 180 to that. 180 plus 21.8. We get 201.8. Now, technically, that answer is fine. There's nothing wrong with it. But does anybody notice anything about it? I wouldn't mark that wrong. It's just you haven't been as kind of clever as you could be. Look at those two expressions. Yeah. Well, what's the first, let's just take the first expression. Okay, we call this expression 1 and this expression 2. If you let k equal 1, what do you get for an answer in the first expression? If you let k equal 1 and do the arithmetic, what do you get?
201.8.
You get 201.80. These are the same thing. This is like if I said to you, make a list starting from the number 3 of all the multiples of 3. Or I said to you, make a list starting from the number 6 of all the multiples of 3. Those are the same thing. Every number that I can get in this list, I can also get in that list. They're the same lists. Let k go from negative infinity to infinity by integers, and do the same thing here. You just picked a different starting point. That's all. So technically, all you need to say here is the first one. You don't need to say the second one. Now, that didn't happen on the last one. These are totally different answers. If you start making a list of all the numbers in the first equation, or first expression, and all the list of the numbers in the second expression, there will never be an overlap here. They're all unique from each other. But here, they all overlap. Okay? And the other reason you might think of that too is think of the graph of tangent or cotangent. I don't care where you put a horizontal line, it's never going to hit that graph more than once per period. That's how I was looking at that, and I knew if they're saying there's two different answers per period here, between those dotted lines, you're never going to get two answers. You're only going to get one. So I knew they had to be repeats of each other somehow. Okay, so there's a lot of stuff to think about in this section. It's definitely a higher level section that kind of pulls together lots of stuff we've learned so far. Okay, any questions on that one? Okay, if you look in your book, they did most of these problems in radians. We did it in degrees. So just pay attention to which degrees or radians they ask you to use. Okay, it's on 394. It's going to have you guys try 37, 38, 41, 42, and 44 to 53.